Welcome back. In this lecture, we'll be addressing the issue of convective mass and membrane transport. In a series of previous lectures, we have analyzed how to simplify the complete set of equations relevant to electrochemical transport. We simplified the set of equations via a variety of approximation. In some cases, we created situations wherein we can neglect migration, where migration is only important. And we also saw simplifications born out of having a binary electrolyte. Okay, all these things was covered in previous lectures. In some ways, this is the last lecture in this series. We would be looking at situations wherein we can model the convective mass transport via empirical correlations and mass transfer coefficient. And we will look at certain aspects of transport involving electrochemical membranes. If you create situations wherein we can suppress migration, okay, so that is possible if you use excess supporting electrolyte. This is often done in industrial situation because you want to avoid ohmic drop or the ohmic O potential. So there are situations where migration can easily be suppressed. The many design principles that have been generated in the context of chemical reactor design can be extrapolated to electrochemical reactor design. Okay, so that is the broad theme for this lecture. In reality, the reactors have fairly complicated geometries. It is not possible, in general, it's not possible to analyze them from first principles, even though the modern tools of computational fluid dynamics is making that possible. So often we rely on empirically generated correlation. We'll see what exactly we mean by that. So the central concept here is we'll be utilizing the so-called mass transfer coefficients. So there is this molar flux that is of interest. This is a central quantity which we have been addressing in the series of lectures. We are going to compute this quantity using this mass transfer coefficient. Okay, so this is a vector quantity. In this definition, there's no, this vectorial sense is not clearly seen. So you have to get the fluxes right, or the direction of fluxes right, you have to really make sure that which is being subtracted from what, whether this is the equation or the other way. Okay, so that will determine the direction of fluxes. Okay, in any case, we are going to use something called this mass transfer coefficient, which is defined within this equation. And again, just to emphasize, this is used when there is no migration, okay, or migration is marginal. So how do you get mass transfer coefficient? This is where correlations come into play. Okay, so via dimensional analysis, you can relate certain dimensionless quantities. This you must have seen in your engineering classes, transport phenomena classes. How do you use dimensional analysis to relate different dimensionless groups? In this case, 3 dimensionless groups are utilized. Sherwood number, which is defined in the following manner: mass transfer coefficient times characteristic length divided by diffusivity. This is the Reynolds number. Then this is the Schmidt number, where kinematic diffusivity divided by mass diffusion coefficient. Okay, that's the way you define Schmidt number. So even though dimensional analysis will tell you which of the dimensionless quantities are related to each other in what manner, it doesn't really tell you the coefficients. Okay, so from dimensional analysis, you may arrive at something like this. However, the dimension analysis doesn't tell you what are the constants here, A and B. Okay, so the coefficients, exponents also are not provided from a dimensional analysis. So you typically have to do a variety of experiments to fix these coefficients and experiments. So because of the importance of the mass transfer coefficient, especially in the context of chemical reactor design, lots of experiments have been done to develop correlations. However, you need to make sure these correlations are well tested, the accuracy, whether they are reasonable for the situation at hand. And then using them, such empirically developed correlations, you can fix the Reynolds number and the Schmidt number, and from there you can get the Sherwood number. So then the molar fluxes are obtained using the Sherwood number, the value of Sherwood number of relevance for your particular system. Okay, so this is incorporated into this equation, and you get this equation. Often, what we are interested is in running the reactor at limiting current densities. At limiting current densities, the concentration of the relevant species at the surface of the electrode is 0. Therefore, this equation reduces to this, the current equation reduces to this. This is the limiting current density. This is the maximum current that can be obtained from the reactor. So the situation we are thinking is that there is a reactant in the bulk which gets transported to the electrode surface and which reacts. Okay, so at limiting current density, Ci surface is 0. Therefore, the limiting current, which is the maximum current that can be obtained, is given by this formula. We also utilize mass transfer coefficient in the context of natural and free convection. So you might have read about natural and free convection in your classes on heat transfer. There, in contrast to forced convection, for example, in forced convection, you impose stirrers and certain other mechanical procedures to improve your convection pattern. But in natural convection or free convection, the reason for convection is temperature difference. Okay, for example, if you have a surface which is at a higher temperature, that would generate circulation patterns or convection patterns. And what is indicated here is the velocity profile that is generated to regions of higher, due to the presence of regions of high differential temperatures. Regions of, when your system has liquid exposed to different temperatures, there are some natural convection patterns that are being set up. So what is the context for of these natural convection in the context of electrochemical reactors? The reason why we are discussing temperature here is that similar effects what are the similar effects? The temperature induces density differences. Okay, so the density typically decreases with increase in temperature, because of which there are natural buoyancy forces, because of which there is convection pattern. So the reason for natural convection is the density differences. In the context of heat transfer, these density differences are generated because of differences in temperature. But in the context of electrochemical reactors, the density differences is because of difference in the composition of the electrolyte. Okay, so supposing at the electrode surface, certain reactions are introduced, which would introduce a density difference, which will set up a circulation pattern. So again, the dimension analysis will tell you that the Sherwood number is connected to Grashof number and Schmidt number, where Grashof number is given by these quantities. Okay, so it tells you, it gives you the Grashof number is a measure of two quantities. The two quantities are, the numerator is a measure of buoyancy forces. The denominator is a measure of viscous forces. So this is again kinematic viscosity. This is density difference. This is the density at the bulk. And again, this is the characteristic length, which is often the size of the electrode that is that is in your reactor. This is the gravitational constant. So this is the density difference that can exist between the bulk and the electrolyte near the electrode surface. Okay, so what was the analogy with heat transfer? In heat transfer, you have a surface that is at, let's say, higher temperature. Okay, so liquid near the electrode surface is warmer than the liquid away from the electrode, away from the metal surface, because of which there are circulation patterns. This gives you the velocity, velocity of the at the boundary layer. So these you must have seen in heat transfer. We are using the analogy between temperature density differences induced by temperature to density differences induced by an electrochemical reaction. So again, in the absence of migration, these kinds of arguments can be utilized to get the mass transfer coefficient, and you can model transport in the electrochemical reactor using such notions. Again, all these empirical correlations have to be tested for their validity. Lot of these research was done in early 80s, and there are some specialized books that deal not only with these correlations, but also how these correlations and mass transfer coefficient can be applied to electrochemical reactors. A system of great relevance to electrochemical reactors are gas evolving system. For example, one of the most important electrochemical reactor is a simple water electrolyzer. Okay, so here you split water and generate oxygen and hydrogen. At the two electrodes, both electrodes involve evolution of gases. What is shown here is evolution of gases at one of the electrode. So there are three phases that are involved. Okay, gases that are generated due to the electrochemical reaction. There is, of course, a solid phase, which is the electrode, and there is this liquid electrolyte. The generation of gases themselves would generate convection patterns, And these are very common in many important practical electrochemical systems. I mentioned electrolyzer. There is also this chloralkali systems, wherein again gases are evolved. So these are all of great industrial importance. So lots of correlations have been generated. Okay, so I'm just mentioning one such correlation where the correlation is documented based on certain characteristic length scales that are present in the system. For example, this H is the distance between two electrodes, this is the length of the electrode, and so on. Okay, so this lecture or this course cannot really do justice to multi-phase modeling of electrochemical reactors. This is a topic, a separate topic dealt with in chemical engineering. Multi-phase flow and multi-phase reactor design is a topic by itself, requiring a separate course. But in case you deal with such systems, there are some specialized books in chemical engineering dealing with multi-phase reactor design. And there are some books in electrochemical engineering that deal with these kinds of concepts. You can go and read them to see how you use these correlations to get the mass transfer coefficient and how do you model them. Okay, so we're not going to elaborate anything further on this topic, but just your textbook also gives you references that you can read to understand this topic in greater detail. We're just providing an exposure to this topic. Moving to a different topic, often you would see these terms used in electrochemical literature. These are three different objects: separators, diaphragms, and membranes. We'll just introduce descriptively these topics and certain concepts that are utilized involving certain concepts of relevance to electrochemical transport. So in a typical system, if you have, let's say, two electrodes and electrolyte in between, the concentration profile is something like this. Often you want to use something more than just the electrolyte to separate the two electrodes. For example, if you have, let's say, a battery, you impose certain mechanical effects to, for example, in this case, contact spring, to keep the distance between the two electrodes the distance is rather small, and there is some kind of a pressure that is imposed by this contact spring. Okay, so these are tightly packed. When you have such large electrodes separated by a small distance, you want to avoid an accidental shorting of the two electrodes. Okay, so to avoid the accidental shorting, what you tend to do, you use a separator, okay, a finite thickness, which would prevent the shorting of the two electrodes. Okay, so the separators have macropores, wherein these macropores are filled with electrolyte. So in this system, there is no separator, but here in this separator, you have filled these macro pores with an electrolyte, and the concentration profile is something like this. Okay, so a diaphragm is a closely related object wherein you use something like a separator to, but probably of a smaller pore size, to separate two solutions of different composition. Okay, so that is the difference between a separator and a diaphragm. So sometimes the two compartments, the anode compartment and the cathode compartment, might be very different, and you use a diaphragm to separate the two compartments. For example, this such kind of so that's just a name. And there is another more important concept of selective membranes that is also used in electrochemical reactors. For example, what is shown here is an electrodialysis unit. So what does this do? You typically use an electrodialysis unit for desalination. Okay. So without going into the working principles of these desalination units, what is to be noticed is that you have brackish water, that is water that is not fit for drinking, but it has certain, because it has higher salinity, so you want to desalinate, that is you want to remove NaCl from the brackish water and generate water that is fit for drinking. So it is again an electrochemical unit. There are electrochemical reactions, in this case hydrogen evolution on this electrode, and on this electrode oxygen evolution. Okay, so when oxygen evolution occurs, there is, let's say, proton generation. In this case, you can imagine this compartment becomes more positively charged, and chlorine minus from this compartment will get selectively transported across this membrane. Okay, so these membranes are physicochemical components that can transport ions selectively. These are anion and cation exchange membranes. So, for example, this membrane would allow only anions to get transported, specifically chlorine minus ion, Cl minus ion, to get transported. And this membrane, which is different in composition from this membrane, will allow for the transport of only Na+. So if you look at this compartment, Na and Cl minus, Na plus and Cl minus are transported into this compartment. So this compartment will get more concentrated, and this compartment will get less concentrated. So this has a series of compartments and alternate compartments, this, and this, have electrolytes wherein Na and Cl minus, Na plus and Cl minus have been removed. And these compartments are concentrated with NaCl. Okay, so this was explored extensively in 70s and 80s, but for desalination. But even though there's a lot of interesting electrochemical science and engineering involved, this is, in terms of cost, this is not cost effective compared to reverse osmosis. That is much more cost effective for desalination of water. But of late, how to stabilize how to generate and stabilize these kinds of membranes are becoming, a lot more research is being done of late. But what I want to emphasize here is the nature of these membranes. These membranes are used for selectively transporting ions. The most popular membrane is called the Nafion membrane, which is a proton selective or cation selective membrane, often used in fuel cells and water electrolyzers. The concentration profile in such a membrane, ion selective membrane, is something like this. Okay, so I want you to contrast three concentration profiles. So to analyze the concentration, you use certain laws involving partition coefficients. Okay, so this were originally generated to look at transport in biological membranes. Okay, so when there is a membrane, in the case of biological system, there was a bilipid membrane, and species gets partitioned. Okay, so the partition coefficient is defined in this manner. That is the concentration, let's say in this phase, divided by the concentration in the beta phase. You are talking about the CI, which partitions between two bulk phases. This is one phase, beta phase. The CI beta is given here, and CI alpha is the concentration here. And there is a discontinuity in concentration at this boundary. Okay, so there is no discontinuity in this case and in this case. However, there is a discontinuity in this case. These are often documented, empirically studied, and can also be modeled based on partition coefficients. Okay, so again, you have to go and take a class in mass transfer. You might have already taken such classes, and such concepts are also utilized in modeling transport across membranes. Lastly, there is also transport of gases via thin films and membranes. For example, in fuel cells, this is of great importance. The way a fuel cell works is that hydrogen, for example, in this case, it's a hydrogen fuel cell. The reactants, so-called reactants, are hydrogen and oxygen. They undergo an exothermic reaction to generate water. This is one of the cleanest electrical power generating device, not limited by Carnot efficiency. It's just like a battery, wherein a battery is a batch reactor. Here a fuel cell is a continuous flow reactor. So this is a battery wherein the reactants are continuously supplied. So hydrogen comes here, you have formation of water, and on this side, air comes in, oxygen from air is utilized for electrochemical combustion of hydrogen, and some spent air gets out. Okay, so the hydrogen fuel cells are typically operated at a temperature of around, let's say, 70 for a variety of reasons. So some water vapor also gets out here. So there are lots of issues related to mass transfer in this case. So hydrogen and oxygen, or air in this case, have to be first dissolved in liquid films that exist here, okay, before they can be transported to the electrode surface. So there is gas phase reactants which dissolve in the liquid phase, and then within the liquid phase, they are transported to the electrode surface, wherein there is electrochemical reaction. For all these systems, you use what is called the Henry's law. Okay, so Henry's law tells you, connects few quantities. This is the partial pressure in the gas phase. For example, I can be oxygen. This is why I indicates the partial pressure of oxygen. Xi is the mole fraction of oxygen in the liquid of interest. This is the Henry's law coefficient, and this is the permeability coefficient. Sorry, this is the pressure of relevance. Okay, so I mean, intuitively you can see this in the following manner. For example, Yi times P gives you the partial pressure of the relevant species in the vapor phase, and Xi gives you the concentration of species I in the liquid phase. This just to correct myself, this is the total pressure, not the permeability coefficient. So all these things have to be first empirically modeled. Okay, so Henry's law. Okay, so or Henry's correlation. Okay, again, these are not laws as fundamental as Newton's law, but these are of great practical relevance. These kinds of approaches are utilized for modeling transport of gases via thin liquid films. Another concept that is utilized is the concept of permeability in membranes. So often when you are having a membrane, for example, in this case, some amount of transport, for example, of oxygen can also occur via the membrane to this compartment. Okay, so you want to suppress that, and to analyze them more quantitatively, you use this concept of permeability. Permeability depends upon two quantities. One is diffusivity and solubility. Okay, first the oxygen, for example, have to get dissolved in the membrane of interest. So that depends upon the solubility coefficient, and once they are dissolved, they get transported by molecular diffusion. So that depends upon diffusivity. So there are two ways to suppress transport of gases across the membrane. Either you can suppress solubility of the gases in the membrane of relevance, or you can suppress diffusivity, or you can do both. Okay? So permeability depends upon diffusivity and solubility. Okay? Diffusivity, if the diffusivity is higher, the permeability is higher. If the Henry's law coefficient, which also shows up here, solubility depends upon 1 divided by Hi, okay, or it's inversely proportional to Henry's law coefficient. Okay, so if Hi is if Henry's law constant is large, then the gas will be mostly dissolved in the membrane and it won't get out. Okay, so if you want to increase permeability, you want to have an optimal solubility. If it's too less soluble, it won't even first dissolve. Okay? Or if it's too high solubility, it will dissolve a lot and it won't get up. Okay, so the way to think about permeability is that, or if you want to suppress transport or increase transport, in any case, you have to think about two quantities. One is, in a way, a property of thermodynamics, solubility, And another is the transport property, diffusivity. So the way to think about permeability is that the gases first dissolve and then get transported. So there are two coefficients of relevance. One is the diffusivity and is the Henry's law coefficient. Okay, these are again well documented in the context of chemical engineering, because these kinds of multi-phase systems are of great relevance in separation systems and chemical engineering. These are complex systems in often requiring a lot more lectures for a thorough understanding of these systems, which these are beyond the scope of this particular course. All I want to say is that these kinds of issues are all also of relevance to a quantitative understanding of electrochemical systems, multi-phase electrochemical systems. So you can appeal to chemical engineering literature and obtain correlations and conceptual guidelines to model these systems. Let us just pause for a minute and see where we are and how we got here. Few lectures ago, so we had introduced all the governing equations for relevant to electrochemical transport. First, there is this molar flux equation, which gives you the quantitative expression for three mechanisms of relevance: migration, diffusion, convection. This you might have already seen in your fluid mechanics class. In mass transfer class, you would have seen diffusion. What is quintessential to or unique to electrochemical system is this migratory transport. Even though this is central to electrochemical systems, this is often suppressed so that we can just deal with diffusion and convection. We introduce equations connecting molar flux to current, because this is what is being measured of most interest to electrochemical systems. And then we had also introduced the mass balance equation. And then there was the electroneutrality condition valid in the bulk of the electrolyte. Many of these quantities are coupled, and even though we can formulate the problem with these set of equations, to solve these equations, a variety of approximations need to be used. Okay, so we first introduce approximations or experimental situation where we can neglect concentration variation, and we can reduce the set of equations to just the Laplace equation, wherein only the electrochemical potential is of relevance. Then we eliminated migration effects using supporting electrolytes, and that gave rise to a simplified set of equations. In the previous lecture, we looked at simplifications from binary electrolyte. In this lecture, we are dealing with this set of simplification. We are utilizing the mass transfer coefficients to model transport. This is the way we define mass transfer coefficient, and we emphasize that to get the value of mass transfer coefficients, dimensional analysis and empirical correlations that have been developed in the context of chemical reactor design can be utilized. So you're often suppressing migration, which makes electrochemical systems unique. You are suppressing migration via supporting electrolyte. Once you have suppressed migration, the system is very similar to what you have in a chemical reactor. Okay? So the differences in an electrochemical reactor and a chemical reactor become marginal. And so many of the correlations that are generated in the context of chemical reactor design can be utilized to get the value of mass transfer coefficient, and you're going to obtain molar flux and via Faraday's law current to model transport. Okay, so this concludes this series of lectures wherein we try to give an overview of different approaches and approximation simplifications involved in electrochemical transport. Thank you.